morning, everyone, and welcome to the Thursday CEDAR plenary session. I'm Federico Gasparini. I'll be chairing this morning session. We will begin today's program with the poster prize announcement, and then several highlights showcasing the breadth and depth of the CEDAR community. This includes the CEDAR Prize Lecture, which recognizes outstanding contributions to the CEDAR science and community leadership. And following that, we will have an early career speaker as well as a science highlight. I'd like to bring to your attention the fact that we will have a range of CEDAR breakout sessions, but then also at 10 a.m. During the breakout this morning, there is a special session on compassionate leadership for burnout, which will be held in room 305, 306 downstairs. This is open to all participants and runs in parallel, as I said, with the breakout block. And the session trains leaders how to recognize and help mentors. And you're welcome to join. It's open to all. In the afternoon, the joint plenary on community care continues this theme, and it's also open to all. And if you're interested in participating in the small group coaching session at 4 p.m., that's unfortunately already booked up, and that's reserved for people with less than 5 years of their PhD. For those with greater than experience, at 5:15 p.m., we have some openings still present, I think 7 or 8, so you're welcome to join. It will be on a first come, first serve. Let's see. So with that, we will begin with the poster prize announcement, which will be given by Titus Yuan. And please, Titus.
Oh, it's here. Okay. Good morning, everyone. So we had a really successful student poster competition session. First of all, I want to thank all the volunteers to judge these more than 100 student posters in the competition. They dedicate their time in their busy schedules to look at all these posters carefully, and we had an open discussion about the top posters. The decision is not easy to make. The poster session for both they run all the way until 9:15 p.m. So we really have a careful and sort of comprehensive discussion of all the posters. And I also want to thank Maggie and all the UCAR staff to arrange the posters in this hallway, arranged in such a way that it's easy to be located and see. We finally want to thank this amazing lady. She seems to have endless magic out of her pocket. Every time we have some weird request, she will always say, yes, I can do it. So Bea, where's Bea? Where is it? Yeah, give a big round of applause to Bea. Yeah, that's because this year we implement the electronic ballot for the first time, so I was both excited and nervous. First time is always a little bit nerve-wracking, but we did it, and the electronic ballot is a huge success in my opinion. So let's see, where is it? Okay, so we this is slides I just made up, made the last night around midnight. So we have 107 students in competition, including 12 undergrads, and these undergrads' work is shockingly good, high quality. that actually give us some hope, meaning that we have flesh blood coming in to push the around community forward, even during this difficult time. Let's see. So now, let's go to the Tuesday winners in the competition. The honorable mention ITIT 32, Brenna Roy Smith. I hope I pronounced the name correctly. So if I didn't, title is integrating new GSS method in 3D ionospheric imaging, a simulation study. And the second place winner is the second place winner is Chen Yifei from CU. The title, What Mechanisms Are Responsible for the Difference Between Boulder and McMurdo? And the first place, MUTR4, James Monaco from CU, specular meteor radar performance and the coverage qualified using Monte Carlo simulation. And for the undergrad award, Polar 5, Michael Landquist from UCLA, a statistical survey of lifted F2 layer peak in the polar cap ionosphere observed by Pfizer North. All right. Okay, so I'll go on. So Wednesday competition, we have the honorable mention Alana Cardenas or Tool, University of Michigan, mutual evolution of plasma density and temperature within super EFPs. Second place, okay. Second place, EQIT4, Aaron Kirkman from Cornell University, short-term evolution of the pre-reversal enhancement as observed by ICON. And first place winner is the EQIT4, Alexandra Green from Boston University, modeling excuse me, a syncretation from E-region plasma instabilities. For the undergrad award is MITC7, Josh Houghton, University of Calgary, formation of continuous emission structures associated with the aurora. So the winner can come upstage. I'll hand out the certificate and take pictures. No? Okay. No one? It's too early, I guess, for a student. Oh, we have one, two. Okay, good.
Okay, our next speaker is Professor Jens Oberheide, and from Clemson University, Department of Physics and Astronomy. Jens is an expert on satellite data analysis and empirical modeling of atmospheric tides, particularly in the mesosphere, lower thermosphere, and ionosphere system. He has led numerous CEDAR workshops, including the current Grand Challenge, with focus on the impact of terrestrial weather on the ionosphere and thermosphere. Jens' research spans tides, planetary waves, gravity waves, and their role in vertically coupling and the geospace dynamics. Work central to understanding how the atmosphere from below influences the space environment. And so we're very excited to award him with the CEDAR Prize Lecture, which honors outstanding contributions both in scientific discovery and community leadership within our program. Jens is a close colleague and also an excellent mentor to a number of students at Clemson, so I'm very much honored for his, as part of the CSSC, to order him, and we look forward to his presentation. And with that, please join me in welcoming Professor Jens Oberheide.
Thank you, Federico, for the nice introduction, and good morning, everyone. So I'm a data analyst, and what I want to do in this lecture is to give you kind of a very broad overview of how far have we actually come to study and to understand global scale waves, in particular tides and planetary waves, how they vary on time scales that basically range from a couple of days to subseasonal, and perhaps most importantly, how do they really impact the ionosphere and thermosphere system. So when I prepared this lecture, I realized this is actually the fourth CEDAR Prize lecture on tides and planetary waves. And I must say both Maura, Jeff, and Ruth set quite a high bar for this type of lecture. So Ruth Maura now roughly 20 years ago talked about the principles, the basics of tides and planetary waves. It's the first modeling efforts. Jeff then introduced what tides do in terms of producing complexity in the ionosphere and thermosphere system. And a couple of years ago, Ruth reported on recent mission progress from the TIME satellite and also from ICON. And so what I'm trying to do in this lecture is to basically talk a little bit about the how so, which means how do we actually observe tides and planetary waves on weather-like timescales from space, and perhaps more importantly about the what for. So what do the tides and planetary waves on these timescales actually do to the ionosphere, and what are the implications for predictability of the ionosphere and thermosphere system? So, I mean, in the CEDAR community, we are all familiar with atmospheric waves, and so just briefly, planetary waves on the different scales, gravity waves, tides, and planetary waves, essentially provide the forcing from below to the IT system, so competing with the forcing from above, from the sun and from the magnetosphere. And what I'm particularly interested in is basically what happens here on this one. Oops. Okay, so it's basically how do the global scale waves, the tides and planetary waves, imprint variability that comes from tropospheric weather or variability in the stratosphere, so variability originating in the lower part of the atmosphere, how do they imprint that on the ionosphere and thermosphere system? So this is more a little bit of a very general energetic perspective of global scale wave coupling. So what you are looking at is the result of empirical tidal modeling driven by timed observations in the mesosphere and lower thermosphere region. And what you see is the global annual mean vertical flux of energy that comes from upward propagating tides. So that's really what atmospheric tides transport energy-wise from the troposphere and stratosphere into the thermosphere. And this includes all the migrating and non-migrating tides, diurnal and semi-diurnal tides. And you see that around 100 kilometers as a kind of a crossover point. Below 100 kilometers, the diurnal tides dominate the energy transport. If you go into the thermosphere above 100 kilometers, it's all dominated by the semi-diurnal tides. And we talk about roughly, in terms of global wave power, 5 gigawatts around 100 kilometers. So, I mean, earlier this week, we talked a lot about the importance of VLEO, so the very low Earth orbit, the increasing importance of VLEO and for orbit predictions, satellite operations, in particular in the age of the mega constellations. So we will most likely have way over 100,000 satellites orbiting Earth 10 years down the road, or perhaps even earlier. And so this view graph basically indicates how important global scale waves from the lower atmosphere, tides and planetary waves actually are for both the deorbiting of spacecraft, but also for predicting the position of spacecraft in the very low Earth orbit. So the top view graph, color-coded, that's basically tidal density perturbations from my empirical tidal model. And some colleagues from CU Boulder basically flew a satellite through this density field. And you see dashed and solid lines there, so basically 3 consecutive orbits. So in case you can't see the scales there, the horizontal axis is latitude, the vertical axis is from the ground to 150 kilometers. And one of the satellite trajectories is computed with tides from the lower atmosphere, and the other curve is satellite trajectory without tides from the lower atmosphere. And you see that for the deorbiting process, the tides change roughly by, or the tides change the footprint of the deorbiting satellite by roughly 15 degrees latitude, so 1,500 kilometers or so. So in my opinion, the really relevant graph is the one in the bottom. So this is a predicted orbit position of a satellite in a very low Earth orbit at 200 kilometers, computed with tides from the lower atmosphere and without tides from the lower atmosphere. And what's plotted there is the difference in position after 24 hours. So basically what you see here is that if we don't get the tides included, or we get the tides wrong in the very low Earth orbit around 200 kilometers, after 24 hours, when we do a satellite orbit prediction, we are wrong by 15 kilometers, and that's quite a bit. And I think this study that Leonard and I did 2012 also gives very strong support for the need to actually measure the tides and the planetary waves in this part of the atmosphere around 200 kilometers. We don't have these observations, as we all know. Precise global scale wave observations, tides, planetary waves are absolutely necessary to do a reasonable job in terms of orbit prediction. So I think this is the real reason why we need a mission like Dynamic, for example. Okay, so tides vary on various time scales. I mean, they have seasonal variations, interannual variations, but they also vary on what I call weather-like time scales. And that's what you see in the top graph here. These are basically 25 years of tidal observations from CEDAR. You're looking into equatorial results, tidal amplitudes at 110 kilometers. So that's essentially what the tides do in the E region. So getting short-term variability out of spaceborne observations is hard. It requires some assumptions, so I'm not going into the details here, but for this particular tidal component, which comes from tropospheric weather processes, with some assumptions, one can actually get a temporal resolution of a couple of days. And with that, we can actually look into what kind of variability really happens in tidal activity, and that's in the wavelet spectrum on the bottom here. And you see the tides vary with the solar cycle. They vary due to El Nino, La Nina conditions, for example. The QBO plays a role. QBO and El Nino talk to each other. We have annual, semi-annual, and seasonal variations, which is basically forcing into circulation effect. And then, and that's highlighted in red and in the blue here, we also have very significant variability occurring on sub-seasonal timescales. So on order 1 to 3 months, this is an effect from recurring tropical convective systems called the Madden-Julian oscillation, and also variability that happens on timescales of a few days. So basically the imprint of tropospheric weather system interactions with planetary waves, but also the response of the tides to the strength of the polar vortex, for example. So now, how do we actually observe short-term tidal variability from space? So this is basically what we can do from a single satellite that is in a low Earth orbit and precessing a little bit. I plotted here the analysis for the MIGHTY instrument on the ICON spacecraft. It's pretty much identical if you look into SABRE data, TIDY data, or other satellite observations. So on the left, I plot all the temperature observations MIGHTY did at 97 kilometers altitude, and I plotted here 35 days of observations. So I just collected all data and plotted them as a function of latitude and of local time. So you can probably see a kind of a sine, cosine looking pattern on the left. That's basically individual orbits from the satellite. And if you collect 35 days of data, the orbit precession basically then fills all of the local times. So then if we just pick a certain latitude range, that's the center panel, so just around 20 degrees latitude, and we then plot all the observations as a function of local time, that's the y-axis, and longitude, that's the horizontal axis. You see that when we combine 35 days of data, we basically have the whole longitude, local time frame completely filled. And so that then allows us to do a very straightforward projection into Fourier space. It's a straightforward two-dimensional Fourier transformation, and that gives us what you see on the right-hand side, the tidal spectrum as a function of zonal wave number, that's the horizontal axis, and as a function of period, this is the vertical axis there. And so what that really means is, if you see amplitudes or phases, tidal amplitudes and tidal phases from a single satellite, you always look into averages In the case of what I plot here for MIGHTY, 35 days. If you do that for CEDAR, that would be an average over 60 days. So in the ionosphere, we can do a different approach, because in the ionosphere, we actually have satellite constellations around. And so a very, very powerful data set and tool for ionospheric studies of global scale waves and tides and short-term variations is the COSMIC 2 constellation. So COSMIC 2, these are 6 satellites that are around 530 kilometers orbit height. And these satellites are in 6 different orbit planes that are 60 degrees apart in longitude. What that really means is that this satellite constellations provides 12 local solar time measurements every single day. And this is enough to actually do tidal fits on a daily basis. And very convenient data set from COSMIC 2. It's called Global Ionospheric Specifications. That's essentially an assimilation or assimilated data set using mostly COSMIC 2 radio occultation measurements supported with GNSS data. And what that provides are hourly maps, global maps. That's what you see on the lower left, longitude versus altitude. Hourly maps of electron density profiles, basically from, I think, around 150 kilometers up to 600 kilometers every single day. And so using satellite constellations like COSMIC 2, we can actually do tidal fits every single day. And that's what you see on the right-hand side. That's a time evolution, basically 3 years of tidal observations for a semidiurnal tide plotted as a function of zonal wave number on the vertical axis. So that means to really measure tidal variability on shorter time scales, what we really want to do is to fly satellite constellations like COSMIC 2. Unfortunately, we don't have that in the neutral atmosphere. There are some special cases where one can, for example, combine data from CEDAR on the TIMET satellite with MLS temperature observations on the Aura spacecraft to get some information, but that's limited to special cases. One can do some assumptions, which basically means one argues for physical reasons certain tidal components or planetary wave components should be dominant over others, and do a short-term tidal diagnostics. That works reasonably well for a number of components, but it does not work at all for other really important tidal components, so it really has limitations. Or finally, one can try to do some statistical approaches that have been tried. And so I want to briefly talk about the statistics of short-term tidal variability, focusing on the mesosphere and lower thermosphere, and how do we actually do that from observations from a single spacecraft, here from for temperature observations from MIGHTY on the ICON spacecraft. Okay? So what you see here is are temperature measurements from MIGHTY at 97 kilometers at 20 degrees north. And it's plotted, the temperature observations are plotted as a function of longitude, okay? And I plotted all the observations for a time period of 35 days. That's the vertical axis, okay? These are really the raw data. And then to identify global scale waves, that's what I'm interested in, tides and planetary waves. One can basically do zonal wave number 0, that's a mean, to zonal wave number 4 fits to these observations that essentially eliminates gravity waves and other sources of smaller scale variability. And the variability you see here is basically induced by both a local time variability, because the vertical axis, that's day of year, but every single day of year has a slightly different local solar time because of the satellite precession. Okay. And so variations you see here are caused by both local time variations and the true change of tidal amplitudes and tidal phases. Okay? So, but a few minutes ago I showed you how we can actually produce 35-day running mean tidal amplitudes and phases, so average amplitudes and phases. And so I can use this information to basically reconstruct the temperature field as a function of longitude and local time. That's what you see here. And because over these 35 days, the amplitudes and phases are constant, the variability you see here is just a straightforward local time variability. And that means I can finally difference these two fields. And this gives me the true day-to-day variability that comes from changes in tidal amplitudes and tidal phases. So that's the information I'm really after. And from that, one can compute a standard deviation. And because one knows from the 35-day average tidal diagnostics how much signal comes from what tidal component, one can then split that into individual tides. And that's what you see here. These are just a few examples. Different tides plotted as a function of latitude and day of year. So that's 1 year, 2020 here. The top row are tidal temperature amplitudes, and the bottom row is the corresponding standard deviation within a 35-day running mean window. And as a rough number, the short-term tidal variability, and that includes everything from timescales between 2 to 35 days, is roughly half of the magnitude of the amplitudes. And this is very similar for other diurnal and semidiurnal tidal components. And now, what's the impact on the ionosphere from that? And the scientific goal here is really to understand how does short-term tidal variability causes, for example, some kind of a preconditioning of the ionosphere so that the ionosphere responds differently to, let's say, more geomagnetic activity or enhanced solar activity. And to do that, my colleague Qian Lu at Clemson University, she's the PI of an NSF Answers project that basically has exactly that as a goal. So use global scale wave observations, also gravity wave observations, put that into the lower boundary of TIE-GCM, and most importantly, not only kind of average field, but really the variability of these observations, run the model, and with short-term variability, without short-term variability, and then see how the model really reacts to different levels of solar and geomagnetic forcing. Okay? And so Qian found, as I think, a really smart way to actually incorporate the short-term variability, the statistical variability I showed you from ICON into TIE-GCM. It's basically constructing a lower boundary time series with day-to-day variability that uses an interior point optimization approach, which works really well. And that's what you can see here. So the bottom row are TIE-GCM results driven by mighty tides and their variability. And the top row are observed cosmic 2 variability, standard deviations in electron density. And you're not looking at tides, you're really looking into variability of tides here. So the left column is the mean state, then the second column is the migrating diurnal tide, then DE3, and finally a semidiurnal migrating tide. And first of all, this shows, and this is all electron density at 300 kilometers, so this first shows that we successfully incorporated observed lower boundary tidal variability into the TIE-GCM because it really compares well with the observed variability in cosmic. And so we have now a setup that will actually allow us to look more closely into how important is this kind of variability actually in terms of understanding the response of the ionosphere to magnetic and solar forcing. So move on to predictability potential of tides, and I want to briefly talk about sudden stratospheric warmings. So sudden stratospheric warmings is a split of the polar vortex, which basically changes the mean circulation and the temperature in the stratosphere. And sudden stratospheric warmings are predictable roughly a week or two in advance. Okay. And so this is what stratospheric warmings do to the composition in the thermosphere. So this is from the gold instrument O2N2. It's basically plotted as a function of latitude, the vertical axis, and for a few months around the winter 2019 stratospheric warming. And what you see is that during the stratospheric warming indicated by the black line, so these are stratospheric winds, we find a depletion of the mean state, the zonal mean O2N2, by roughly 10 to 15%. And so this was predicted by model simulations before. This is, to the best of my knowledge, the first observation and confirmation of these model predictions. So what really happens is, from Larissa's groundbreaking work, we know that the tides, semidiurnal tides, are much bigger during stratospheric warmings. So the bigger tides cause an enhanced wave driving. This changes the residual mean circulation in the lower part of the thermosphere, which in turn changes the concentration of mainly atomic oxygen in the lower thermosphere, and then molecular diffusion basically distributes the change in composition throughout the whole thermosphere. And finally, that's what we observe in a NADAR measurement in the O2N2 column density measurement. So this is an example for the F-region ionosphere response. This is from Cosmic 2. That's mainly work that my student Deepali Agarwal did. So we are looking into the January 21 stratospheric warming, and what's plotted as a function of latitude are electron density amplitudes from cosmic at 300 kilometers. So the top panel is the semidiurnal migrating tide, so that's a solar tide. It's mainly a consequence of enhanced zonal winds in the E region, what you see, so mainly a dynamo process. And on the bottom, Deepali was able to separate the lunar tide, the M2 lunar tide, from the solar tides, and that's plotted here. And in both cases, you see that the tides significantly enhance during the stratospheric warming. And physically, something different happens there. So the M2 lunar tidal enhancement is more a resonant amplification of moving a so-called Pecker's resonance in the mesosphere towards the period of the lunar tide. And Deepali has to talk about that later today, if you're interested into some details. So this is a little bit of a time evolution of the lunar tide. So the animation in the top is altitude 200 to 600 kilometers as a function of magnetic latitude. And you see the enhancement of the electron density, and we are talking about roughly 15% with respect to the mean state, persists throughout the whole bottom and top side, and you can even see in the top side when the two crests merge that we still see lunar tidal enhancements here during the stratospheric warming. And again, strat warms can be predicted 1 to 2 weeks in advance, and that means this kind of variability can also be predicted 1 or 2 weeks in advance, at least in principle. So then I want to briefly talk about a similar physical process, also tidal enhancement related to polar vortex variability, but outside of stratospheric warmings, because the strength of the polar vortex can also be predicted 1 or 2 weeks in advance. And that's what you see here. This is again on the top, a time series of cosmic 2 tidal observations in the ionosphere at 300 kilometers. And the correlation plot there basically compares the magnitude of the ionospheric tides with the NAM index. So the NAM index is a measure for the strength of the polar vortex. If you have a large negative NAM index, then you have a very unstable vortex. And if you have a positive NAM index, you have a very stable polar vortex. So during the stratospheric warmings, very low NAM index, you have very strong tides. So the purple points here. Then if you plot in the same winter the tidal amplitudes outside the stratospheric warming, you see that they kind of scatter around a line, okay, depending on the strength of the vortex. The same is true for the year 21-22, the winter, where we had a very stable vortex. And we actually have a very clear anti-correlation for tidal activity in the ionosphere with the strength, the stability of the polar vortex during low solar activity. So if you now go to a year where you have more solar activity, 22-23, you see, well, that looks different. So all the points are below the line, obviously less correlation here during solar activity. And so Dipali looked into the reasons for that. So the top plot is what I just showed you, same color code. The center plot is a simulation from Wacom, okay, for the same conditions. And you see the model actually does a really good job reproducing the relationship between the stability of the polar vortex with the ionospheric tides. And the bottom plot is a Wacom simulation with constant, very low solar conditions, so 70 solar flux units for all years and very low KP index. And you see that that actually causes all the data points again to lie on a line, so with a high correlation. And so what really happens is if you have a high solar activity, you have a hotter thermosphere. A hotter thermosphere means you have more tidal dissipation because it's proportional to the temperature, which in turn causes smaller tidal winds in the E region, which in turn causes smaller vertical drift velocities, which in turn causes smaller electron densities in the F region. Okay. So I think I'm running out of time as expected, so I only want to spend a couple of minutes talking about planetary waves here in the F region ionosphere. And I want to focus here on planetary waves with periods 2 to 20 days, so basically traveling planetary waves. So that we see planetary waves in the F region ionosphere is actually complicated. These planetary waves should not really easily propagate into the thermosphere and into the E region. So I don't want to go into the details here, but it's basically, from a dynamical point of view, the consequence of a second-order planetary wave tidal interactions to map the dynamical signals into the dynamo region. And then once you have these dynamical variations there, then again they map through similar mechanisms as the tides into the plasma. And also planetary waves are moderately predictable a few days in advance. And so this is how it looks like. Top plot is from our gold observations. These are not highly analyzed data. These are basically raw observations, NMF2 at 75 west and 19 local time as a function of time and latitude. Then the center panel are GNSS TEC observations, same time and latitude. And the lower plot are planetary waves, the 6-day westward propagating zonal wave number 1, planetary wave observed in temperature data from CEDAR in the mesosphere lower thermosphere region. And so that's a paper that Chuan Gan did. Most likely coupling mechanism here is, as I've already said, E-region dynamo, but most likely there are additional coupling processes that play a role that are not that well understood. And in this particular case, it looks like that a tidal wind modulation of pre-reversal enhancement of vertical ion drifts might also be important. So one can also look into planetary waves in the cosmic data. This is basically amplitudes of the 16-day wave, 300 kilometers from cosmic, plotted for 1 year as a function of latitude. That's work of my graduate student, Sona Baiju. And the problem, if you look into planetary waves in the ionosphere observed from space, you can't be entirely sure that this is driven from below, because you also have the same kind of periodicity that comes from the sun or from geomagnetic activity. And so that's what the two wavelets plots there show, particularly in the second part of 2020. There was 10.7 NKP activity that also happened on the same kind of time scale we observed planetary waves. And so Sonar developed a wavelet filtering technique that basically allows to remove solar and geomagnetic effects from the observed planetary wave signals to really clearly identify what is really coming from below, okay, in terms of ionospheric response. And that is basically the planetary wave spectrum in electron density for April 2020 from Cosmic 2 on the left-hand side. So plotted are amplitudes relative to the mean. So every individual planetary wave has roughly 5–6% variability. And that actually compares very well to model simulations that Jeff Forbes did a few years ago. And these are the same solar conditions here, even if these are different years. And I really want to draw your attention to the zonally symmetric vacillations I pointed out there. I think that's a really interesting and not really understood feature, because zonally symmetric oscillations can't be an E-region dynamo effect, because we don't have any kind of current divergence that's produced. And so it's both in the observations, it's in the model simulation, so the model is able to reproduce that. It's not really clear what's happening. There are different possible explanations there. Probably everything kind of contributes, but I mean, Han Li did a paper about short-term tidal and planetary wave activity in 2010, where he kind of suggested that zonal asymmetries in conductivity may play a role, and that's my feeling is that it's probably one of the important factors there that need to be investigated more closely. And so, coming to my take-home points here, so the F-region ionosphere really responds very strongly to short-term tidal and planetary wave variability. So we are talking about changes relative to the mean electron density of 40, 50, 60%, so it's not a small effect. We can actually map these variations conclusively through tides and planetary waves from tropospheric and stratospheric sources into the ionosphere, and a particular radio occultation data from Cosmic 2 are really a great tool to study that. And I also think that this kind of observation kind of provides at least a framework for predictability. So I showed you the results for stratospheric warmings and vortex variability. Didn't show you examples for the Madden-Julian oscillation, but that's kind of similar. these lower atmospheric variabilities with advanced numerical weather models, they can all be predicted 1 or 2 weeks in advance, okay, and with a good quality. And so that means if one now couples a numerical weather forecast model, and I mean, Valerie Uden is kind of working on along those lines, we actually have a tool, if we couple that with whole atmosphere models, to really have a predictability tool there, in particular during low solar activity. But I also think that from a purely observational point of view, there's a lot of potential applying machine learning approaches in a way that one hopefully can say, well, the stability of the stability of the polar vortex will be that and that in a week from now, and so we expect this kind of a response in the ionosphere, for example. And my last point is, and I really want to emphasize that, what really remains a challenge is the predictability in the very low Earth orbit, so the neutral part of the atmosphere. So tides and, I mean, in all likelihood, planetary waves will definitely have a big impact on orbits. And unfortunately, right now, we don't have measurements in the relevant altitude region. That's, we have empirical modeling, and sometimes the model is good, sometimes it's not good, or we have a general circulation model, but as long as we don't measure that, we can't really solve the problem and produce better orbit predictions. That's really why no matter what, a mission-like dynamic is really absolutely necessary, not only for scientific reasons, but I think also for operational purposes. And with that, would like to acknowledge support from NASA and NSF, and all the support I got from my students, my postdocs, and a lot of other people in this room. Thank you.
Great. Thank you, Jens. That was an excellent talk and overview on tides and planetary waves. And I particularly appreciated your comment on predictability, which I think is particularly important in the days where we are living now, where it's very important to demonstrate impact on society. So with that, I think we have time for maybe a couple of questions. We'll run the mics on this side of the room and the other side. So who has any questions? See Ruth.
Thank you, Jens. That was great. So my question is about the slide that showed the semi-diurnal tide and the lunar tide response to the warming in the electron density. It was a vertical, a latitude-altitude plot. An animation. Yes. So it seems that the response is stronger in the northern hemisphere latitudes. Is that related to the fact that the warming is located in the northern hemisphere, or what?
I don't have a good answer to this question. That's, I mean, it always looks like that. So first of all, perhaps for those of you who are not really so familiar with the global coupling. So tides are a truly global effect. So if you change tides, let's say in the northern hemisphere, because we have a stratospheric warming, that will basically map globally, because this is a global response. So from this perspective, the response should be kind of symmetric, what one might expect. Obviously, it is not symmetric. What the detailed reason for this asymmetry between the northern and the southern hemisphere is, I don't have a good answer to that. I think that still needs to be explored.
Yeah. Okay, thank you.
Thanks, Jens. That's a really interesting talk. Your first plot showed the strength of the semi-diurnal versus diurnal tides as a function of altitude summed over the planet. I know all the way to slide 2. So I didn't know that.
This one?
I'm actually shocked by this. and I've been thinking about it ever since. If you split this between, if you showed a few more plots like migrating versus non-migrating. I mean, I think this is a dominant migrating.
Yes.
This is the migrating tide.
Yes.
So if you took out the migrating tide, how would this change? And of course, also look at it as a function of latitude. Wouldn't that change a lot as well?
Yeah, so first of all, so that's all in all these plots you are asking for are in the paper that my student Mukhtar recently published. So, but in short, yes, the global wave power is dominated by the migrating semidiurnal tide, but there are also cases during certain months, this is just an annual mean here, where actually the non-migrating tides have a pretty big impact. There's also a seasonal variation going on, some response to the solar cycle, for example. And what was the last part of your question?
Latitude.
The latitude, yes. So there are, of course, latitudinal differences. I mean, what Mukhtar is, so my student is looking into right now is, for example, the contribution from horizontal transport, which of course is kind of zero or almost zero if you're looking into a global mean, but where there's a lot of latitudinal dependence. So yeah, there's a lot of latitude dependence, yeah.
Okay, one last question. I see here, Sharon.
Oh, thank you for that. So on this plot, this is for upward going tides from the lower atmosphere, but there's also the in situ generation from the sun, which I'm assuming at some point, maybe 150, 160 becomes larger than the stuff coming up from below, as well as potentially in situ generation of gravity wave dissipation. And I'm just wondering if you can ballpark estimate for us on this graph where the generation, for example, solar input would come in and where it would be dominant.
Yes, so the in situ forcing becomes dominant above roughly 120, 125 kilometers and really starts to ramp up. I truly appreciate your comment about the potential gravity wave related forcing. That's something where Mukhtar has started to look into using the high resolution vacuum simulations. Potentially, if we see something there, that's with standard resolution vacuum, there's no way to look into that. But yeah, the in situ forcing is important, and also in terms of tidal heating rates, for example.
Great, thank you. Let's thank again our speaker and invite him to stay on stage because we have a certificate.
Yep, thank you, Jens. I would just like to add my own comment that every time I look at papers or presentations on tides, I see all these color figures full of complicated reds and blues and splotches, and half the time I can't tell exactly what I'm supposed to be looking at. But you just did a beautiful job of making that really clear and understandable, and I think I followed everything you said, so that was quite the achievement to get me to understand it, so thank you for that. And so, as is our tradition, on behalf of the CEDAR Science Steering Committee, we would like to present you with a certificate to recognise the significant honour of giving this prize lecture. And it was a good one, and I particularly enjoyed it, so thank you.
Thank you, Mark.
Yeah. And I will just add that it's been my pleasure in the last year or 18 months to work with Jens on another project, and he really is a leader in the field, and he's done a magnificent job of leading that group. So we've got a really deserving speaker this time, so thank you.
Thank you.
And with that, I'd like to introduce our early career speaker for the second early career science highlight, which is given by Shun Xiao, and the title of her presentation is Wave-Wave Interactions and Modulation in the Mesosphere and Lower Thermosphere. We very much look forward to this presentation. Please, the floor is yours.
Good morning, everyone. This is Shun Xiao from NCAR HAO. I'm currently an ASP postdoc there. First of all, I really appreciate this opportunity provided by the CEDAR Science Steering Committee for having me speaking here. And I would really like to acknowledge my collaborators, co-authors for this work. Without their contribution, it couldn't even be possible. So today I'm going to talk about a case study during the 2019 Southern Hemisphere SSW. I could also call it Antarctic SSW. We look at the wave-wave interactions modulation in the MLT region across the scales of planetary wave, tides, and neatly including the gravity waves from observation. So I always like to start with this illustration to show how SSW are strong dynamical disturbances to the whole atmosphere. It produces anomalous temperature response into the mesosphere-thermosphere, and it also produces a lot of wave activities. And sometimes we can observe the planetary wave periodicity in the ionosphere. And the question is really, how could this planetary wave periodicity penetrate into it, because it could not directly propagate upward, so upward into the ionosphere. So possible mechanisms include the planetary wave modulation on gravity waves, and gravity wave can propagate upward. Also, planetary wave interact with tides, and the secondary wave could propagate upward and then in turn generate the planetary wave periodicity in the ionosphere. So that's the possible mechanisms we're going to discuss today. So the first question would be, why this specific SSW? As a background knowledge, we know that SSW more often happen in the northern hemisphere. It's in average happening 6 times per decade. However, SSW is very rarely happening in the southern hemisphere because of the stronger or more stable polar vortex in the Antarctic. So this 2019 SSW, Antarctic SSW, really provides a unique case to focus on. And we also happen to have observation during this time. So, and we also know, and it's reported previously, and also is also mentioned, during this SSW, the 6-day wave is greater than the average in September. Qiangan did work, and there's also others' work to report this activity in the MLT region, also the periodicity in the ionosphere. What we can tell directly from the radar observation, how it works, if we look at the meteor radar meridional wind, we can see the quasi 6-day periodicity response in the raw wind itself. And it's also, the periodicity is very clear in the swarm TEC, that the peak is showing about every 6 days. And GOLD and GNSS, and also I think CEDAR also shows the similar wave activity. So the question now really becomes, what's the underlying mechanism for this upward propagation? And we mentioned that tides could play a role, gravity wave could also play a role, so let's see what we do about it. So we combine a pair of meteor radar at 30 degrees south to first diagnose the zonal wave number of the 6-day wave, and then we will put an emphasis on the corner meteor radar wind because this is a modern developed meteor radar. It has very high meteor detection, and so that we can play with the data more often to push it more than the traditional zonal meridional wind, but also diverged wind, vertical winds, and temperature as well. So something else very specific about this radar system is it has a very high detection power, transmitting power, so that gives us the very high meteor detection rate as well. So I steal this plot from the Condor PI's, the Condor website. And so when we did this work, it was only 3 sites. Well, I shouldn't say only, but it was 3 sites. Currently, there's a 4th site coming in, and there's a 5th site will be deployed later this year. And I would like to point to Alan's talk later in the Grand Challenge graduate session to hear more about this radar itself. So with this very high meteor detection rate, about 100K or even exceeding 100K meteor detection per day, we could push the observational resolution to look at finer structures, and including the individual gravity waves. So Gunter Stover developed an algorithm called 3D wall, sometimes plus dive, to look at the word here is a bit corrupted, but to look at the diverged wind field and the tomographic reconstruction of the diverged wind field. The temporal resolution could go high up to 3 minutes, and standard 5 minutes, 10 minutes, and 30 minutes are also possible. And the spacing could go up to 30 by 30 kilometers. So that's really fun structure can be looked at, and I think Alan will include some new research topic on this. So really for this study, we used some, but not all of the modern techniques. So specifically, we used the temperature derived from the bipolar diffusion coefficient, and we also look at the gravity wave wind radiuses and momentum fluxes from the 3D wall algorithm that Gunter developed. So with the zonal meridional winds and temperature component of the 6-day wave could be computed, we could also calculate the momentum flux and heat flux of the 6-day wave, and that with some approximate assumption, we can get the EP flux, a local EP flux, time average EP flux at the of this 6-day wave activity, and we could talk about the relative importance of heat flux, momentum flux, and say how if there's enhancement of this EP flux of the 6-day wave. So, so a combination of the 2 meteor radar wind is shown here. The 2 meteor radar has the overlaying observation of 10 days. I'm showing the meridional wind component here, and combining these 2, fitting the 6-day wave out, and assuming which zonal wave number propagation is, we could figure out what is the best aligned with each other, and we can tell that this westward wave number 1 propagation. I also reconstruct the 6-day wave at different level. We could get the vertical wavelength of the 6-day wave is roughly 67 kilometers, which is aligned with the theory that the 6-day wave has a long vertical wavelength, roughly about 60 to 70 kilometers. So we could also take the wavelet analysis, more like wavelet analysis on these periodicities. And it's a basic plot. I'll try to walk it through. The 1st, 3rd, and 5th row are the periodicities between 4 and 10 days. So a closer look at the 6-day periodicity, the 6-day wave in meridional wind, zonal wind, and temperature correspondingly. So as we can tell that the 6-day wave activity is strong before, during, and after the SSW max warming time. The max warming is indicated by the white vertical line here. And also, we can say that with the curved lines showing the components in meridional wind, zonal wind, and meridional wind temperature, we can say that it's getting in phase after the SSW max warming time, and the in phase relationship gives you the enhanced momentum flux and and heat flux of this 6-day wave, so that we know that there's potential energy coming into this 6-day wave, makes it long-lasting and persistent during this SSW time. And what's in particular interesting is that we also say if we zoom into the 24-hour period and we plot the absolute amplitude of this diurnal tide, we can see that the diurnal tide amplitude, I should go back. We can see that the diurnal tide amplitude has the quasi 6-day response to it. So basically peak, 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 and 6-day separated. So this itself is a 6-day modulation on tide, and it's also a possible nonlinear interaction, hint for nonlinear interaction between the 6-day wave and tides. And later on, we can say that there's a 21-hour peak, which is the dashed yellow line here, is over exceeding the amplitude of the diurnal tide. So that means the 21-hour child wave is existing, and this confirms the nonlinear interaction, because this period is a period of the child wave of the 6-day wave interacting with tides. So one possible mechanism could be found here. And then something neat about this observation is we can also look at the grass wave response of it, and we can say that the meridional wind variance of the grass wave also has a 4 to 5 days response during this period of time. So there's also possible modulation of the 6-day wave on the grass wave activities. So this is in addition another mechanism for the possible penetration of this 6-day periodicity into the ionosphere. So with that, I would like to conclude this short talk, also short work, that the 6-day wave westward 1 propagation could be identified by combining the 2 meteor radars, and we see this 6-day wave activity is very strong during this period of time. And we also investigated the 6-day wave tide interaction, grass wave modulation at this range in the MLT region, and this provides 2 possible mechanisms for the 6-day periodicity penetration into the ionosphere. So, have a short illustration here to say what's the coupling processes that we're carrying about today. And if I'm even though I'm still not very far from graduation, but I would always like to recall back to the history a little bit. And, this is my first time attending CEDAR, and I attended CEDAR ever since. I really always appreciate the interaction with CEDAR students, and they're so energetic, and they're really a very unique and very welcoming community. So I always enjoy to interact with them. And for my students audience here, if bear with me to share some experience with you, I always enjoyed to interact with our CEDAR scientists as well. And the CEDAR as a community has many resources you can leverage with. Their data from instrument PI, there's also more than algorithm. For example, Gunter's algorithm that I used, and there's also many other resources you can leverage with, and hopefully to shape your own science based on that. So yeah, with that, I would like to conclude and welcome any questions. Thank you so much.
Great, thank you very much for a very excellent presentation. I think we have time for just one question from the audience.
Thank you for that nice talk. I guess my question is more of a broader one. Whenever people talk about tidal modulation of gravity waves, what that equates to somebody like me is dissipation of gravity waves, momentum deposition, secondary gravity wave generation. Some of the secondary waves go up, and then now they dissipate somewhere else, and now they're modulating tides somewhere else, like, 50 kilometers higher, 80 kilometers, 100 kilometers higher, whatever. So the modulation at the lower altitudes end up causing another modulation at the higher altitudes. And I'm just wondering if you can just comment on that.
Yeah, I mean, I have really limited experience, but so based on my analysis, I would say the wind filtering of gravity wave is existing, and so even before the dissipation and generation of secondary waves. And then with the filtered group of gravity waves propagating upwards, and then with later on, secondary wave generation and first wave dissipation, and then I think it's a whole complicated process. Yeah, so I guess I need to talk to you more with the secondary wave. Yeah, thanks a lot for the question.
Okay, thank you. Next, we have another science talk, which will be given by Jia Yui on the satellite drag, and we look forward to continuing that theme that was first introduced by Jens. So please take it away.
Good morning. Yeah, my name is Jia Yui from NASA CCMC. I would first thank the CSSA to invite me to give this. You'll find it very controversial. It's unlike many of the talks you will hear at CEDAR. So talk about how the lower atmosphere may impact the satellite drag and re-entry. So the lower atmosphere here means anywhere below the LEO, where the satellites are flying. So I would first acknowledge my co-authors, especially Jean Brunsma. He's the head of geodesy at CNES, France. This work, we started this collaboration when I visited him at the CNES. It's a beautiful southern France. It's the best place to get out of my comfort zone and ask some hard questions. And also would thank Jack Wang, my colleague, and also Nick Panadella, who provided the model runs. If you know Xiang, he's a very straightforward person. So this talk will be very honest. You may hate it or love it at the end. Okay, when I gave the introduction 2 years ago, that's just my own problem. So Zishun just mentioned her first CEDAR was 2019. My first was 2003. So I've been working on this vertical coupling, wave coupling problem for a long time. And I came from the MLT community. So we wrote a lot of papers about how the waves coupled the low atmosphere to the ionosphere and thermosphere. And NSF requires broad impact. There are a lot of indirect effects, like in Jens's talk and also Zishun's talk. But how about the direct impact? So the MLT is too high for weather, climate, even the ozone hole in the stratosphere. It's too low for LEO. Usually it's 400, 500, even above, and like spread AF scintillation. Except the billion layer and tourism, they tend to go to that region, but only like 10 of them. When I gave this 2 years ago, I didn't think more. But when the fundamental research at NSF is under attack now, I don't think this is funny, because fundamental research, whatever CEDAR is doing, it is critical for the nation. There's a real motivation. I don't have to repeat that there are more and more satellites, like Starlink, are launched into the LEO. So that space environment has become very crowded, and the collision avoidance has been critical. And also the reentry, like not every satellites or even space junk, they burn out when they re-enter the Earth. I learned from Xiang that the satellite re-entry is around 120 kilometers. And this, the left figure is the recent ESA ERS-2 re-entry. This is the shape of the picture of the satellite, and the right one is the trajectory. So below about 120 kilometers, it's just mostly free falling. So for the ESA, NASA, and all those operational offices, they calculate the re-entry around 200, 300 kilometers till it re-enter the Earth. Because they, like Jens just mentioned, the MLT actually overlap part of the re-entry trajectory. So my initial motivation is to find more direct application for the MLT science. To start, is the lower ionosphere significant for satellite drag and re-entry? Just give one example, the indirect effect. This is the Sputnik, that's the human's first satellite launched from Soviet Union in 1957. Just a few years later, the papers were published that the global mean satellite drag, actually you can derive the neutral density from that, shows a very clear annual and semi-annual oscillation. So the minimum of satellite drag is around summer solstice, northern summer solstice. The second minimum around winter solstice. So you can see that very clear on the left figure shows this. This has been haunting the science community for a long time, trying to understand it. Until recently, my colleague Jack Wang, he published a paper at GIL. You can go there. We did the numerical simulation. The purple line is the MSIS. So the MSIS 2.1 from NRL is based on observations, shows very clear annual and semi-annual oscillations of the global mean satellite drag and mass density. And the black line is just the regular TIE-GCM 2.0 run with no information, day-to-day variability of from the low ionosphere. And the recent TIE-GCM version 3 developed at NCAR, it has an option, a function of the lower boundary enlarged by the more realistic Wacom-X, which is the red dashed line there. Once that function is included, it just gives us a much better realistic AO and SAO in the mass density. And all those dynamics, including gravity wave, forcing tides, planetary waves, as in previous talks. But the physics is more complicated, so you have to go to this paper to look at the mechanism. Let's go to the direct effect. So is the lower ionosphere significant for the drag? That depends. It's depending on the altitude and the solar cycle for the day-to-day variability. So this is a numerical experiment we did with Xiang and also with Nick. The secret recipe is Nick did some Wacom-X runs that just keep the F10.7 and KP constant. So we can separate the effect from above. And because Wacom-X is a whole ionosphere model, so it has all the waves from below. So there are several runs. Of course, there are the runs during solar minimum with and without changing F10.7 and KP. We can separate the effects. And also in Nick's paper, he did an ensemble of 40 northern hemisphere winters by introducing random perturbations to the model. So There are SSWs or some other ensembles have very stable polar vortex, which is the opposite of SSW. And we'll also compare with MSIS 00, keep also very low solar activities. And Xiang Brandsma runs the reentry POD, precise orbit determination, from 200 kilometers to 120 kilometers to simulate the reentry. So we just provide the model output to Xiang, and he just run his program through the model output. And the imaginary satellite is polar orbiting, so all the information about satellites there. And this POD includes the forcing of gravity, 3D body, the ocean and solid Earth tides, and the most important, the satellite drag. Sean and I did an earlier paper. This is a little bit complicated mathematics, but okay. So just the left figure just shows the variability. This is the Wacom X1. The variability of mass density, you can translate that to satellite drag at 300 kilometers and 120 kilometers. So if the bar is wider, it means larger day-to-day variability. In this round, just the variability is caused by the solar and geomagnetic. It's about 40% day-to-day variability. And from another round, that the variability induced by the lower atmosphere is about 5%. So at 300 kilometers, it's still mainly controlled by from above, the forcing from above. On the opposite, at 120 kilometers, so the reentry level, they're comparable. So this is 10% day-to-day variability induced by the solar or geomagnetic variability is about 10%. The lower ionosphere variability is about 10%. And in this paper, we also found that we look at the variability from 130 kilometers, 140 kilometers to 150 kilometers. The circle day-to-day variability, those are from solar and geomagnetic. Just increase with height from 10% to 15% to 20%. So it's really during solar minimum, the 120 kilometers and 150 kilometers is a transition from the lower atmosphere forcing dominated to solar and geomagnetic. So this brought us the idea that because the reentry calculation and prediction starts at around 200 kilometers and ends at around 120 kilometers. So there's an overlapping of this transition region. So we want to see how the lower atmosphere dynamics may impact the reentry. And this is ESA satellite trajectory. Here's the statement on their website. I read it through. The reentry uncertainty is largely the result of how difficult it is to forecast the density of the air through which the satellite is passing. Atmospheric density determines the strength of the drag that causes the satellite's orbit to decay. But our ability to predict is limited how well we can model our complex atmosphere and the space weather conditions. One challenge is how well can we predict like solar and geomagnetic forcing for next month, right? The prediction is actually more challenging than we thought. The left figure shows that the prediction happened months before. So you can see the white bar, those are 1 month, 2 months uncertainty, where the reentry could happen. And once it's closer and closer, and the altitude becomes lower, this uncertainty becomes smaller until it just re-entry there. And this is the trajectory, the right-hand side, that's the trajectory of the orbit. So it's a lot of uncertainty. The biggest, we think of the biggest disturbance from the lower atmosphere, just from the past two talks, you can see it's the SSW. I don't have to explain it. So this is the target we're using, and it's based on Nick Panatella's paper. So when we were looking at the Nick's paper, we found out that the SSW and the non-SSW, it could disturb the temperature in the zonal wind up to 200 kilometers, but mostly in the polar region. Of course, the satellite drag, when the satellite is flying, it's not only flying in the polar region, so it has to be global mean. So we're looking at also Nick's paper about the O2N2 ratio, and we know that the O2N2 ratio is highly correlated with the global mass density. And this is the onset, this is a NAM index, and this is the onset of the SSW. You could see the perturbation here from Nick's paper is about 4% of the O2N2 ratio. So at that time, we naturally or naively, we speculated if SSW could impact satellite reentry by changing thermosphere density. So we did more. And this is Nick's run. So he told us there are 40 ensembles. Ensemble 11 it shows very strong SSW in Wacom X. And there are certain ensemble runs, it has very strong polar vortex that is opposite of SSW, so we can do some sensitivity study. And we'll also compare with MSIS 00, which has no consideration of the lower atmosphere. And because the MSIS density is so different from Wacom X, so we scale it by 0.7 to do a better comparison. So this is a result. So for the same satellite trajectory, the MSIS predicted around SSW 5.3 days, and the SSW run pointed about 5 days. And there's other opposite, non-SSW is like 5.1 days. So from this study, the conclusion is the lower atmosphere forcing causes 1 to 2 hours or 1 to 2 orbit uncertainty in re-entry time, or about 2%. So Jens mentioned a paper of 15 kilometer uncertainty caused by tides. This is about thousands, tens of thousands of kilometers uncertainty. But we move on from this study. We want to look at how the realistic situation. So we check we use the SD Wacom DART SSW run in 2009, which is the solar minimum with realistic F10.7 and KP, and compare with MSIS. You can see it's very quiet in KP and not much variation in F10.7. About this SSW event, you can refer to Panatella papers or Harvey paper. This plot just shows the global mean mass density at 120 kilometers. So this is the onset of SSW. So if the satellite reentry happens before SSW, it takes 4.5 days. If it's after, it's 4.4 days. So it changes about 0.1 day change during SSW. And I didn't show the MSIS. Of course, MSIS 00 shows no change at all. But as the reentry code moves higher, the impact of atmosphere becomes smaller. So this is only the 120 kilometers. Okay, so this is probably the most important figure, and this just those figures were produced last week. We also look at the solar maximum. During solar maximum years, this is 2023. Let me explain the curves. So this magenta curve, this is daily F10.7. You can see very clear 27-day oscillations there. The red curve is from TIEGCM. So there's no, except GSWM, there's no other lower atmosphere information there. And this black curve, that's the Wacom X run with realistic F10.7, KP, and also lower atmosphere. There are several things you can notice that when the F10.7 is high, it means larger solar heating, means higher density, and shorter reentry time. So this is very good correlation of predicted reentry time and F10.7 there. Another takeaway message is, so this is Wacom, TIGCM, this is Wacom X. The discrepancy between models are even larger than the drivers. This is my last figure, but sorry for the very crowded, because a lot of information are there. This is a solar minimum. This is that 2009 SSW event. The variation of F10.7, this magenta line, is small. Just compare two runs, because we did a lot of TIGCM and Wacom X calculations. As this dark blue line is with no solar and geomagnetic forcing. It's constant. And the light blue line, that's with solar and geomagnetic forcing. You can see the variations are comparable, even without any forcing from above, from sun or from magnetosphere. So the conclusion here is during solar minimum, the reentry prediction, the scale from the lower atmosphere, like SSW, is comparable. It's about the same scale to the solar and geomagnetic forcing. Again, the model discrepancies are very large. So depending on what kind of model the operators are using, MCS and other models, it will give you a very different reentry time. Okay, here's a conclusion. This study is a result of collaboration between like MLT dynamics and geodesy. It's usually not our common science. The lower atmosphere actually helps to drive the seasonal variations of the thermosphere density and the satellite drag, in additional to the solar heating. So this is also helpful for the predictions. 120 and 150 kilometers during solar minimum is the transition region from the lower atmosphere controlled atmosphere to the solar and geomagnetic. SSW can cause 1 to 2 hours or 1 to 2 orbit uncertainty in reentry time, or 2% of the total time from 200 kilometers to 120 kilometers. For the biggest SSW, 2009 solar minimum, the reentry time caused by the SSW is comparable to the forcing from above. But think about solar minimum, it's half of satellites' lifetime. During solar minimum, maximum, the solar radiation is very, very reversely correlated with reentry time. So we don't think lower atmosphere becomes that important there. And another thing is the reentry time prediction highly depends on the model. the discrepancy is even bigger than the drivers. So depending on what kind of models the operators are using, to give you a very different re-entry time. Okay, that's the end of my talk. Thank you.
Thank you, Gia, for a very nice presentation on a very important topic. I think we have maybe time for one quick question. Before I leave to that question, I have a question myself. I was wondering if you did you look into the Gochi reentry data for 2013 and produced any sort of model data comparisons, since we have very good density product during the reentry?
The answer is no, but Xiang, me, and also the DEF group, we are talking about it. Yeah, it's very important.
It would be very nice thing to
provide some validation.
Yeah, thank you. Yeah, really nice talk. I really like you relate this to the orbital reentry time. So my question is that you compare between solar max and the minimum. You said, of course, solar max, the lower atmosphere effect is relatively smaller, but would it still have the same magnitude in terms of the uncertainty of the orbit, reentry time? You said 1 or 2 orbits, 1 or 2 hours, right? Even at the solar max.
Well, that's a relative question. So I show this figure here. On solar max, the variation of F10.7 is so huge, so the prediction of F10.7 is very difficult. So the amount of uncertainty caused by the prediction of the solar radiance becomes much more important compared to 2% or 1 to 2 orbit.
Our speaker, we should move on since it's time for our break. So please enjoy coffee outside, and the breakout sessions will be at 10, and reminder about the community session also happening at 10.